Okay, perfect. Yeah. Yeah. Hi. Good morning, everybody. Yeah. Very good to be back in Vienna. Like I've been here for 3 years, and so I'm now transitioning to Garching, but it's good to be back. Like one last time, kind of. Yeah. So as Cora said, I will be talking about the Discord DJ code that kind of we've been developing with our group in Vienna here, and so it's actually very nice to see that everybody on this list that is kind of somehow related to Discord DJ and has contributed is here today. So, yeah, I think everybody's here today, so it's actually a nice, also kind of a nice Discord DJ meeting at the same time. So like parts of the code have been published already. So the particle mesh module, which I will focus my talk on today. So I already wrote 2509, so like I still have 1 week to put it on the archive. I had hoped to achieve it before the workshop, but okay, it should be on the archive soon. Right, okay, so I will keep the introduction very short because we've already discussed quite a lot about field level inference and so on. So like after GIS poll yesterday, we all know what it is, or we don't know what it is, depending on how you interpret the results. So Adrian kind of collected the answers on Slack, and it was quite interesting to see. But so we all know that it has something to do with using the information in the entire field, right? Instead of compressing to summary statistics, to get, at the end of the day, to get super tight constraints on parameters, or maybe also just a bit tighter. So this is also still kind of open to debate. Actually, this slide I made before the workshop with these 2 quotes from Min's paper and yeah, from this paper with the kind of contrasting results. So we've already discussed about this, but I still thought I'd leave it. Yeah, but okay. In any case, like no matter what we will gain at the end of the day with field level inference, what we need to do it and to explore it and so on is forward models, right? So okay, so my talk will focus on a specific forward model. And so okay, let me maybe go back a bit to kind of the big picture of forward modeling the large scale structure. So what you would typically do is, so you start with your set of cosmological parameters, and then with a white noise field initialization that basically kind of describes the initial density fluctuations, right? Okay, so then what you need is a linear power spectrum, which you would usually compute with, CAMP class, like with your linear Einstein-Boltzmann code. Once you have this, you can kind of convolve the white noise field with this power spectrum to get kind of a field that has this linear power spectrum. Then you need to evolve it forward in time, right, to get kind of the late time matter field or on the light cone or whatever you're interested in. Then the next step is basically to get your observables, right, kind of with a bias model or with HOD or whatever you want to do. And kind of once you have this, so then this is kind of your model of what's happening. And then you can go back all the way. So we've already heard in Carolina's talk, and Thomas talks a bit about kind of the different ways of doing it with explicit inference, for which you need derivatives, right, kind of to run your HMC chains, or with implicit, so SBI kind of inference, and then you get whatever you're interested in, parameter constraints, or also samples from the initial conditions. Right. So this Codice is kind of one framework that we've been developing to kind of implement such a pipeline, right? And so kind of what it contains at the moment, right, is a linear Einstein-Boltzmann solver. So this one is, has already been published. It's already available also publicly to be used. Then we have LPT at arbitrary order, so kind of as derived by Cornelius and Oliver, for example. So this is a bit in the spirit of left field. So you could, if you want, you can also compute 5 LPT and so on. Then we have a quantum physics inspired what is called propagator perturbation theory that Cora worked on quite a lot. And so we have kind of theory informed particle mesh simulations where we use these theory informed time steps, such as, for example, BullFrog that Cornelius talked about yesterday. Right, and we implemented quite some discreteness suppression techniques. I will tell you more about these later. And so kind of for those of you who kind of know a bit more about the details of kind of how backpropagation works to compute derivatives, right? So kind of, and what you want to do is kind of as you increase the number of time steps, you want the memory load, like in particular if you do it on the GPU, to be consistent. To be constant. Yeah, for the backpropagation, right? And so one nice way of doing this is kind of what Yin Li et al. Came up with by using the adjoint method, and so we also implemented this, right? So basically, kind of the memory load of computing derivatives is independent of the number of time steps. Yeah, so in this Codice, kind of we use JAX, so some of you might know it, which is basically a Python library that runs on GPU and is automatically kind of auto-differentiable. right? So you can do, in discrete, you can do forward mode autodiff, reverse mode autodiff. So, and you can, of course, also easily interface it with, samplers, blackjacks, numparo. You can also use it to generate a large suite of training data for doing implicit inference. And so then there are also many things that are kind of currently in the making, like going to multiple GPUs. So Lucas is working on this a lot. Getting realism into this observables and so on. Okay, so let me start with the linear Einstein-Boltzmann solver, right? So kind of going from cosmological parameters to your linear power spectrum. So, so if you include massive neutrinos, as we do, then kind of what you need to do is you need to solve a kind of coupled system of like on the order of 100 stiff ordinary differential equations, like if you do it in Fourier space for each k-mod, right? And so because it's stiff, kind of what you would usually do is you would use an implicit time integration scheme, right, for stability. And for these schemes, what you need is basically the derivatives, so the Jacobian. So kind of if you use a framework such as, for example, in JAX, where you can use autodiff to compute a Jacobian, that's actually quite convenient, right? Because then you don't need to use fine differences to solve the integration in time, but you can simply get a Jacobian with autodiff, right? So it's quite nice. Okay, so here these are the results in comparison with Camp and class, right? So okay, yeah. So what basically, I mean, it does what it's supposed to do. So you get your power spectrum with an error of much less than 1%. Yeah, and I mean, so yeah, and so it runs on a GPU. It uses, as I said, it uses autodiff for the Jacobian instead of fine differences. And so if you're interested in using it, so if you ever need a kind of differentiable Einstein-Boltzmann solver, then check it out here. It's publicly available. Okay, so then what you can do is you can, of course, you can take a look, for example, at derivatives of the linear power spectrum with respect to different cosmological parameters, right? As a function of scale, as a function of time, which is kind of quite instructive. So you see kind of when recombination is happening and how it affects in different scales, right? So I mean, you can just, I think, even visually, you can learn quite something from this. But of course, you can also do kind of, let's say, quantitative science. So for example, this shows now a Fisher forecast for Euclid spectroscopy. And I mean, so you all know kind of for Fisher forecast, what you need is kind of the response of the observable with respect to varying your parameters, right? So in this derivative, kind of because the Einstein-Boltzmann solver is differentiable, this derivative is automatically computed with autodiff, right? Which is very convenient instead of finite differences. And you see that it agrees quite well with the official Euclid paper here. Okay, so enough about the linear evolution. So kind of I will now switch to nonlinear evolution. So kind of once you have the linear power spectrum, right, then kind of now you're interested in kind of going to the late-time field, basically. And so just to repeat, so what we currently have in this code is so we have LPT, then we have this quantum-informed PPT, and we have particle mesh simulations with these theory-informed time steppers. So just as a quick tease, kind of what the results look like. So this is like full n-body, you know, like 3 p.m. gadget 4, 100 megaparsec per h-box at 2 different times, so at redshift 3 and redshift 0. So these are the kind of our perturbative methods. So this is only 2 LPT, but we could also do, 5 LPT or whatever. So what you see basically is kind of for the perturbative methods here at kind of early-ish times, you see it kind of visually it agrees quite well as you would expect. But then at late times, I mean, this is kind of way beyond the perturbative regime, right? So you see that kind of the structure is kind of with LPT is completely smeared out. Or with in this quantum-based PPT, you get these interference patterns, right, which is completely expected. But so if you do, for example, particle mesh, then you see even at redshift 0, I mean, because particle mesh kind of it's in the limit of infinitely many time steps, and infinite resolution is still kind of UV complete, right? So you can access non-perturbative scales, of course. So even if our time integrators are kind of perturbation theory informed, right? Yeah, so you see visually, even at redshift 0, it looks quite good. Of course, so like one important aspect when using simulations in the context of inference or like, say field level inference is so how do you reduce the number of time steps that you want to run, right? Because you don't want to run 1,000 steps, then back propagate through 1,000 steps and so on. It's just way too slow and too expensive. So like we've already heard now, yeah, in Ashton's talk, right now, also in Florian's talk about Cola, we've heard quite a lot about this. Okay, so what you can't do is you can't just say, okay, you run your standard code, reduce the number of time steps to 10 or something, and then you take the results, right? I mean, so you see, if you do this, you do form like a small-scale structure, but it's completely misaligned with the with what you would get with a proper simulation, right? Because kind of this doesn't have any information about kind of cosmic growth built into it. So like I will quickly repeat this plot that Cornelius also showed. So what we're doing in discrete is we use this BullFrog integrator, which is basically has 2 LPT built in, right? So this combines the benefit of LPT on large scales, that it gets large scales right, with kind of the fact that in the simulation you basically then you kind of form the small scales correctly, right? And so if you do it together, and even if you do, let's say, only 10 steps and you compare it to a standard simulation with 1,000 steps, you see it matches actually quite well. Okay, so another important aspect I want to stress is, I mean, okay, in the context of field level models, right? I mean, I think one important aspect is also kind of to compare different models at the field level, right? Because if you want to kind of discuss which forward models should be used and so on, but we all look at a power spectrum, I mean, it's maybe not enough, right? Because if we want to do field level inference, then we should also know at the field level kind of what's going on. So kind of like one interesting test is, for example, so if you now run one single BullFrog particle mesh step from a super early time to still another early time, right? And compare kind of where LPT is still valid, and you compare the results with LPT, kind of then you might expect that you see, okay, BullFrog is at least as accurate as 2 LPT or something, maybe a bit more. But what you see is that the residual is completely swamped by noise, right? Because I mean, in n-body simulations, everything is discrete with particles, so basically you don't see anything, right? So this makes it super hard actually to compare, let's say, n-body simulations with perturbative methods. So, okay, sorry. Yeah, this is just for visualization. Basically, you don't see any difference between the different LPT orders. So this is the only takeaway from this. No, it's not accurate. I mean, so my takeaway is basically that the particle noise is in orders of magnitude bigger than kind of the differences between the different LPT orders. Yeah, I mean, it's not meant to be. I have another plot that shows how you can still do it. Okay, but so this kind of what this motivates is kind of that we implemented into discrete quite kind of a suite of discreteness suppression techniques. So one of them is kind of that you can use higher order mass assignment kernels, right? So kind of, I mean, usually people would probably use CIC, but so kind of also interesting in the context of inference, right? Let's say if you want to use the Newton method or something that gives you second order convergence, then also this assumes higher order differentiability, right? So also in this context, it might be very useful to actually go to a higher order for the mass assignment, TSC, PCS, and so on. And something else that we implemented is kind of to kind of conceptually even do without any localized mass assignment. But what you can do is you can basically compute the density contrast in Fourier space, and just by kind of extending the definition of the Fourier transform to kind of non-uniform particle positions. So I mean, so this formula looks like a standard Fourier transform, right? But with the discrete Fourier transform, but with the difference that these are really kind of the particle positions where they are in space, right? So it's not a grid, but it's just, and so this formula just basically gives you directly the density contrast without localized mass assignment conceptually. And so this is also quite a useful technique. And what we also have implemented is the aliasing with interlaced grids, but basically where you kind of compute the acceleration first on this grid, then on the slightly shifted grid, and you average the two. So this you can show that this suppresses the kind of the most important aliases. And then we also implemented the sheet-based particle resampling technique, where basically what you do is in the force calculation, you spawn new artificial particles, right, that live in Lagrangian space between your actual tracer particles. Then you interpolate the displacement from these particles to the new artificial particles. So you get kind of you get basically an approximation of the gravitational potential that is way less discrete and noisy, right? And so let me now jump back kind of to this idea of kind of comparing techniques at early times and so on. So kind of one thing we were then wondering is, I mean, so kind of given that we have 2 LPT built into a time integrator, into BullFrog, right? So can we simply, like, do we even need LPT at all to run a simulation, right? I mean, so usually you would start a simulation with 1 LPT or 2 LPT at some high redshift, and then you would switch to n-body, right? So this is how you would usually do. But then, so kind of we wondered, can we just go to redshift infinity, so kind of scale factor 0, right? because like all the variables used by BullFrog, because it works in terms of growth factor, they remain bounded at time 0. So can we simply start our simulation at that time, right? Okay, so I can show you the results. So if you do this, if you use some of these discreteness suppression techniques that I just showed, and you do a single BullFrog step from redshift infinity basically to redshift 18, and then you compare the displacement field between the different LPT orders and particle mesh with these discreteness suppression techniques. So now you also even see a color bar with numbers. I hope it's appreciated. Then you see that kind of even after single step. So basically, you really see kind of now how you can get a simple particle mesh simulation, like with an LPT informed time integrator, in a single step to agree basically with 3 LPT. Right? So kind of if you apply these techniques, what you can do is basically you can start at redshift infinity, and then just do a single time step with these techniques, and it's as accurate as if you had explicitly computed 3 LPT and started your simulation, right? So I mean, from a theoretical point of view, I think it's quite nice, but I think from a practical point of view, kind of something like this is also kind of nice to compare different forward modes, like PM-based versus perturbation theory-based and so on. Okay, but it's very. Am I going over time? Oh, okay. So I don't be very.
How many slides you have?
No, they're only okay. I'll be very quick. So okay, forgetting about all these discreteness reduction techniques. So these are just some results now of the PM code with BullFrog at redshift 0. So just, okay, power spectrum, cross spectrum, and equilateral bispectrum. So with the 25 steps, you get, roughly 1% error at a K of 0.4 at redshift 0. So this is kind of just for you to get kind of as an order of magnitude estimate. Okay, now let me skip this and then straight go to this. So, okay, then what you can do is you can basically differentiate through the entire pipeline, right? So you can now kind of compute derivatives through the linear Einstein-Boltzmann module, through the BullFrog particle mesh n-body, and then, for example, through the bispectrum, right? And so this shows the derivative of the bispectrum with respect to different cosmological parameters. And so this shows the specific case for omega matter in comparison with Quixote. And so and so you see they agree actually very well. And so in discrete you can get this like just using autodiff on a single GPU in less than a minute. Whereas kind of, in Quixote, each Quixote simulation was run on hundreds of CPUs for some hours. You need to run 2 to compute final differences and so on. So for these applications, it's quite nice. Okay, last slide. So this is actually only a very short thesis. So, so in the paper that will hopefully appear on the archive next week, we also kind of investigate a lot of different kind of numerical parameters in force computation, right? So kind of when should you start the simulation, with which LPT order, which derivatives kernel should you use, what about aliasing and so on. So kind of even if you don't plan on using discrete specifically, this might be kind of still interesting. So if you're using a different PM code, kind of just to look into what we find here. Okay, so this brings me to my conclusions. So so as I said, discrete contains a linear Einstein-Boltzmann module plus different nonlinear forward models. It's written in checks and it's kind of everything is differentiable. Something that I didn't say so far is okay. So how long does kind of how fast is the simulation code? So for example, if you use 512 cube particles, which is kind of the limit what fits on one A100 GPU, for example, right? Then so each time step takes roughly 0.4 seconds. So as I showed you, like in many applications, doing 20 steps is enough. So then, in a few seconds, you get actually quite good predictions. So if you want to do inference, let's say explicit with HMC or implicit, it's just you need a lot of training data. You can use discrete for this. And so kind of many people are currently also working on implementing, like going forward with this. So yeah, thank you very much.